We're continuing our discussion of the Compton scattering of a photon by a moving electron. Uh, in the first video, we have used the energy conservation and momentum conservation equations to show that lambda prime, the scattered photon wavelength, can be written in terms of the energy of the electron E, the momentum P, uh, and the wavelength of the incoming photon lambda with this expression. Now, in part A, the second part, we want to show that if capital E is much greater than mc square, where m is the rest mass of the electron, this result reduces to the following expression. So let's look at this limit now. If capital E is much greater than mc square, then looking at our third equation here, the third equation, equation number 3, tells us that capital P times C can be isolated here. Capital P times C is equal to capital E square minus mc square parenthesis square root, and this can be written as capital E times 1 minus mc squared divided by capital E squared to the power 1/2. Okay. So we've taken this into capital E square parentheses, and that's what we obtain. Now, we have the following simplification. Capital E is much greater than mc square, and I recall that 1 minus x to the power n is approximately equal to 1 minus nx when x is much less than 1. So I recall this result from Taylor series expansion. So I'm going to apply that here because capital E is much greater than mc squared. This is 1 minus x. So mc square over E parentheses square is a small number. So this can be approximated to be capital E times 1 minus 1 over 2 m square c to the fourth power divided by capital E square. And you can see that this is equal to capital E minus 1 over 2 m squared c to the fourth power divided by E. So if I look at this term, capital E minus capital P times C, that would be equal to capital E minus capital E. So capital E's would cancel, and then this minus sign would become plus 1 over 2 m squared c to the fourth power divided by E. So let's write that result here. So I have capital E minus capital P times C is approximately 1 over 2 m squared c to the fourth power divided by the energy E. So, and then I have this E plus PC term at the bottom. So for E plus PC, capital P times C, I have E plus E minus 1 over 2 m squared c to the fourth power divided by capital E. And since this term is rather small, I can neglect it. This is approximately equal to 2e. So if I go back to my lambda prime expression, lambda prime is approximately in this limit, I have lambda times E minus PC. For E minus PC, I'm substituting this result. So I have lambda times 1 over 2 m squared c to the fourth power divided by E, capital E. And then I have 2hc here. So this is plus 2hc divided by capital E plus capital P times C. For capital E plus PC, I'm substituting 2E. So this is 2E. And that will give me lambda m squared c to the fourth power divided by 4e squared. That's the first term. And then I have 2hc divided by 2e. So here I have 2hc divided by 2e. That's going to give me hc divided by e. Now I take this into hc over e parentheses. hc over capital E parentheses. Here I have 1. That's the first term. And then here I have lambda m squared c to the fourth power divided by 4e hc. So that's what I obtain for lambda prime if capital E is much greater than mc squared. Okay, so we have we can compare this to the suggested result here, and that's exactly what we have. Now let's move on to part B. A beam of infrared radiation from a carbon dioxide laser, lambda is equal to 10.6 micrometers, collides head-on with a beam of electrons, each of total energy capital equals 10 giga-electron volts. 1 giga-electron volt is 10 to 9 electron volts. Calculate the wavelength lambda prime of the scattered photons, assuming a 180-degree scattering angle. Okay, so we have lambda is equal to 10.6 micrometers. Energy of the electron is 10.0 giga-electron volts, which is 10 times 10 to 9 electron volts times the electron charge 1.6 10 to minus 19 coulombs. That gives us 1.6 times 10 to minus 9 joules of energy. So lambda prime is equal to hc over E, 6.63 10 to minus 34 joule seconds, Planck's constant, 3 times 10 to 8 meters per second speed of light, divided by 1.6 times 10 to minus 9 joules, multiplied by 1 plus lambda, 10.6 10 to minus 6 meters, m squared, 9.11 10 to minus 31 kilograms, rest mass of the electron, times c to the fourth power, 3 times 10 to 8 to the fourth power, divided by 4ehc. So that's going to give us 4 times 1.6 10 to minus 9 joules, Planck's constant 6.63 10 to minus 34 joule seconds, and 3 times 10 to 8 meters per second. And if we perform this calculation, we find the scattered photon wavelength to be 7.08 times 10 to minus 15 meters. That's femtometers. Okay, part C. What kind of scattered photons are these? Infrared, microwave, ultraviolet, etc. Can you think of an application of this effect? Okay, so this corresponds to, if we look at the electromagnetic spectrum, gamma rays. So these are with wavelengths less than 10 to minus 10 meters in the electromagnetic spectrum. We recognize these as gamma rays. So this can be used as a method to produce gamma rays as an application. Okay, so we talked about a Compton scattering of a photon by a moving electron. Before the collision, the photon has wavelength lambda moving in plus x direction, electron moving in minus x direction with total energy capital E. And they collide head-on. After the collision, they move in minus x direction, so 180 degrees scattering angle for the photon. So we've derived an expression for the wavelength of the scattered photon in the limit capital E much greater than mc square. So we found this result in part A. And we do that by writing the energy conservation equation and momentum conservation equation. And then we've looked at, for an incident radiation coming from a carbon dioxide laser, and the electron energy is 10 giga electron volts, the wavelength of the scattered photons, lambda prime, in part B, and we found that that corresponds to gamma rays, so this can be used to produce gamma rays.